So we'll talk about trusses briefly, and then we can do homework. So for our deformation, right, with our last couple of labs, we've kind of proved to ourselves that these work, and we can derive that K is going to equal to AE over L. It becomes our stiffness for our element. And we've been dealing with the one-dimensional spring and the matrix that works for. And we've been doing one dimension, so now we're going to go to two-dimensional translation for our truss elements, X and the Y. So our equation still, basic equation still appears essentially the same. We've just added the Y component, the Y axis now, second axis. So of course our matrix gets bigger, everything gets a little more complicated, a little longer to multiply through. And we're saying that our axis is aligned with the element. But in the reality is that most of the time our global axis is going to be different than our local axis. So to describe that translation from 1 to 2 or Q1 to Q2, we have to include cosine and sine and redo our matrix. And it'll look, our translation matrix will look something like this. Top two rows are identified as the first row is the X, second row is the Y for N1, and then vice versa for N2. But we're not going to go through any of the hand calculations. We're not going to develop any of that. We've done enough linear algebra up to this point as far as you understand what's happening behind the curtain, in the black box, whatever. So we'll just, from here on out, we're just going to work on the application of how we're going to do this. So if we have a example of a truss, which we're doing pin connections for, we can set up our elements and our nodes, draw the object. One of the things that we'll talk about or continually talk about through the rest of this is symmetry. Anytime we can take advantage of symmetry, then we may as well. Saves you in time to put the model together, saves you in time of processing, but we have to be a little careful about how we do that and be cautious in setting up our constraints and loads. So for this, let's assume that at node 2, 4, and 6, we have 5,000 pounds at each one of those nodes. So if we were going to do symmetry, we might set up something that looks like this. So node 2 is going to have 5,000 pounds on it. What's going to happen at node 4? It's going to have half of that, so 2,500 pounds. And we're constraining it normal to our axis of symmetry. Okay, it won't display or it won't displace in our axis of symmetry. And node 5 we had to create for element 6, which is now half as long. But note that element, that big long beam at the top of the truss, is not going to deflect or deform in the y-axis. So we have to constrain that node 5 in the y-axis to behave just like the full truss element would. Okay, does that make sense? Questions about that? Okay, so if we analyze, I mean, this isn't a very big system, and so it analyzes fairly quickly. So if we do the full truss result, then our max displacement is at node 3 and we get, what, 0.16 inches. So now if we look at the results for the half, mislabeled, but anyway, for the half a truss, our max deflection again is at node 3, but our displacement is what? Half of the full displacement, because it's 0.08 as opposed to 0.16. Okay, so we can take advantage of the symmetry, and for many of our models, it'll make a difference and be worthwhile to do so. And you just have to understand how to constrain it and how to interpret your results so that you're treating it as if it was the full piece.